Hello, hello. Yes, works. Okay, very welcome today again. Nice to see you again. You survived yesterday, yes? Okay. I will just start with an introduction of what we are doing here at KTH, a little, very short, just to say something about where we come from. So this is just a picture of Stockholm in the background on KTH. KTH is rather close to the center of Stockholm. So it's just a subway, 3 stations, and then you're in really middle of in the town, into walking distance. This is our president, and this is just to show. And we are working with sustainability, equality, and internationalization. And so we have very many international students at KTH. I think the background is why we are compared to a very small language. So this, because of that, we have all our teaching in English since many years, compared to, for example, Germany and France. They have a lot of teaching in German, also in master level, or in French. And so because of that, it's not so easy to come if you understand French and German. And in Netherlands, for example, I know that they must write the thesis, in thesis sometimes, master thesis in Netherlands. And that is then, of course, it starts to be complicated. But we have been rather international, and we are a big, Sweden is a big trading country traditionally. We have a huge amount of trading. We have big companies as Ericsson, ABB, and so on, and it's international companies. I don't. So we have 13,000 full-time students at KTH, and 1,800 research students, and we have 3,500 full-time positions. So I think, as I understand, this is slightly bigger than this university. Not clear, but anyhow. And we are rather high in the world-class ranking. Of course, we are not MIT, but it depends on what you compare with. In this QS World Ranking, we are 26 in electrical engineering in the world, which is not too bad, I think. So we are, so electrical engineering is rather famous. And that is, let's say, as I understand, this kind of thing is important nowadays for students that are selecting. I got a lot of master students that then, why have you selected the KTH? And then they say, yeah, we looked on the ranking. On the other hand, that is sometimes a bit strange, as I see it, because the ranking is on the research, while they are coming for teaching. So you don't have the ranking in the teaching, but on the other hand, that hopefully they are linked, but not always, I can say, everywhere. So we have one program in electric power engineering, where we have very many students. And it's also like we have, for example, when I teach load flow and we teach load flow and this kind of thing, we have around 70 students in the classroom, and I think 2/3 are foreigners compared to Swedes in that program. So we have very many international students in our area. And especially electric power has increased so much in the last, I mean, it's so lot of things. I mean, you get electric vehicles, so electric power is really coming up more and more as a very big issue in the world now, I think. I mean, if you go back 15 years, when you said that you were working with electric power, the question was more, oh, these kind of old things, are you still working with these kind of things? But nowadays, I mean, electric power, oh, vehicles, wind power, solar power, interesting, you are doing the modern things. So it has really changed in the last, you can call it 10, 15 years, I think. And that is, I think, a difference. I think that's an issue when we have PhD program. In Sweden, a PhD student is normally working 5 years. That is what you're employed for. The reason is that, I mean, I think that you here have this, compared to Sweden, the shorter PhD, which exists in UK. Denmark, for example, our neighboring country, and also Norway have shorter PhD, while Sweden and Finland and Germany have these longer PhDs. Which means Sweden, the standard is that you have a 3-year program. You have a project which takes 3 years full time. But then you also have 1 year of courses. That makes it 4 years. But then you are normally employed for 5 years because you spend 20% of the time helping the department with assisting courses, correcting exams, and so on. So because of that, it's very common that it can take 5 years to take a PhD. And then, of course, you can be slower, but some are also faster. But so that because of that, we all normally have an employment of 5 years, and they are employed, as I said earlier. And so we don't have a, and we nearly, it works like this because I get a lot of questions. Can I get a PhD student? I want to come to your program. But it works like this at KTH, that we always have to have an ID. We apply for funding, and then when we get funding, we hire a person. So I must have a project, must have state subsidy for that specific project. I must have very often industrial support for our projects, and then we can start when we have the funding. So I don't have any, absolutely zero, internal funding for PhD students. So we don't have a program. It's not as master students where you can, let's say, are paid to have students. So it's very different PhDs and masters from our point of view. Just a little about what we are doing in our department then. Sorry. Earlier we had another organization, and then we had something called the Department of Electric Power System, and I was the head of that. But now we have merged this department with other departments, so then I'm not any longer the head, but then we have formed research groups. And so Electric Power Systems is in reality 3 research groups. And I have one of them, and that is Integration of Renewable Energy Sources, IRS, we call it. First, a little about myself. I think I said a little bit earlier, I had my PhD in 1988, and that was also about wind power integration. So I have worked with these kind of things since a rather long time, I can say. And as I said, that during that time, people were just asking why I throwed my life away on these things that will never happen. But then I have started since then, and then I have been supervisor for PhD students since 1996 in reality, and I've worked with rather many issues. So I have, I have more seen the problem as if someone say that, yeah, but if you have wind power, you get problems with something, harmonics, voltage, reactive power, curtailment, markets. And then I say that, you think it's a problem, can you fund a project? And then so I have had projects in rather many issues, power quality, for example, harmonics. Someone said that, but that is not exactly wind power, but everything is of course related, because the way I see it is that solar and wind power is never the problem. That is not the problem is the rest. Solar and wind power is varying, going up and down, and you can have different kind of generators, but then the question is how to manage that using the other sources in the system. So wind power and solar power always becomes an integration issue. So you have to understand all the other power plants. It's absolutely impossible to do anything with wind and solar power if you don't know how to do with all the other issues. So because of that, you have to understand hydropower, power markets, you have to understand power quality, keeping reactive power, and so on. And I work with making my music. That's interesting. Okay. So this is just the current projects we have. So I have had a lot of projects through the years. So these are the postdocs we have right now. I have one, Puria. I will talk about his project because that is very related to what I've talked about now. That is voltage control in distribution grids with, it should be, now I see, wind solar power. With solar power, PV. I wrote this yesterday. Anyhow, this is a cooperation with Germany. So here we have a cooperation directly with a German grid company. So we have got data, which is very nice because it's not so common that you get data from the real companies. But in this case, we get a dig silent file with all the data for a distribution company, also in some parts down to the low voltage grid. And they have, 5 times more solar power sometimes than they have demand in this area. And then the question is how to handle that. And then I see Shahab there. He's called Shahab, but his name is Muhammad. This is not the correct title now, I see. He's working with the flexibility, because the idea is in the Nordic system to increase the flexibility, because in order to integrate more in solar and wind power, you have to integrate that. And then we have two new, this is a completely new project to the right. The idea is to make an open source software, but it's based probably on the new program. I don't know if anyone is working with Julia here. Have you heard about Julia? That is a new tool which is available. It's developed by MIT, and it's a combination of MATLAB. You can do everything, as I understand, in MATLAB. You can do in Julia. It's open source, developed by MIT, and you also have very strong links to optimization tools. They have an optimization package called GAMS, which is very much used all over the world, but that is started to be very old, and it's also cost you money. So the benefit of working with Julia is that it's very fast. We have a program that was done in MATLAB plus Excel plus GAMS, an optimization tool, and then another guy rewrote it in Julia, and it became much faster and object-oriented, so it was very much easy to just take a part of it and so on. And we are going to make that kind of program for more large-scale power system simulation. I mean, simulate operation simulation, load flow, hourly dispatch, and so on. And then these are the current PhD students where I'm the main supervisor for. The first guy up to the left, he's working with, he's in reality employed by the system operator, working with online control of the system. But he's making a PhD. The question is, what has happened, depending both on markets and depending on wind power, is that the frequency is varying much more now compared to, let's say, 5 years ago. The question is how to stabilize that. Should you have more primary control? Should you have more efficient operation? Should you take decisions in another way, and so on? And he's trying to simulate how, he's building up a model, how to simulate that. Then we have there, Lars Herre, a German guy. He's working with demand-side management. The question is, demand side, everyone is talking about demand side. The question is, when do you get the information that you should be, do you get the information, please change? Or do you get the information, can you change tomorrow, perhaps between 3 and 4? Or do you get the information 2 hours ahead? Can you get the information, because when you get more and more wind power and solar power, the interesting thing is to let's say, change, because the forecasts are so bad. So I mean, if I say that it seems like we will not have any wind tomorrow, can you please decrease your demand at that time? The problem is that that forecast may be totally wrong. So why should I plan my? So the demand side management should be how flexible you are is depending on when you get the information. Of course, you can always curtail consumers. And then we have projector is overheated. Please clean the filters. Okay. Elis down there, he's working with curtailment of wind power. I will show you later that if you have large amount of wind power in the system or solar power, you will come to situations when you have a huge, absolutely too much. You have that in all countries with, I mean, you can take countries with a huge amount of solar and wind, Texas, Ireland, Spain, Portugal, UK, for example, and Denmark. I mean, they are curtailing sometimes because you just have so much wind power and so much demand. Of course, you have to curtail. The question is, you want to do it as late as possible and as little as possible, and the question is how you should do it. Should you do it automatically, just measure things, or should you do it with control room things? So that's what he's doing. Egil, he's working with LOLP, loss of load probability, which is a very common thing, the risk of capacity deficit. But the question is that what all methods I've seen so far is that you calculate it for one area. But then the question is that you can have many areas with limited transmission capability. For example, in Sweden, there's a discussion that we may get problems if it's not windy and not sunny. Yeah, but then we can import. Yeah, but we don't know if you can import from the other area because it depends on if it's windy or sunny there. And then you start to think about, you have to match that in some way. And that is what he's working with. Stefan is working with this project that I showed you yesterday, transmission system reactive supports from wind power in other grids. And then we have Evelyn. She's working with a project. She's continuing with a project that we have started with earlier. The challenge is that when you are going to simulate big areas, let's say size of India or size of Europe or something like this, you cannot have exact detailed models of each hydropower station which is linked to the next hydropower station. It's impossible. So then you have to make equivalents. So you simulate you lump them together, and then the question is, how should this do in order to be a good way? Okay, so that was just very short about what we are doing. So then I continue with what I started with yesterday. This was my house, or is my house. Not only was, but it was in January. Yes, so this was the variable production that you can have, which is significantly varying. And then you can see, now we come in more into voltages. What is nice with this converter is that a huge amount of data is stored. What is stored is in reality, as I see it, a huge amount of data. I calculated it, and you get millions of data points. Because what they are storing is, for each 5 minutes, they are storing voltages in the 3 phases. It's a 3-phase converter. Voltages in the 3 phases, currents in the 3 phases, the DC voltage on the DC side of the converter, and the DC current on the feeding side, and the power. And I think they get 10 things or something that is stored every 5 minutes. And then I answered, but where is it stored and how much can you store? And they told me that that is stored in the converter. And they have storage enough for 7 years of data. And then they start to write over what you had earlier. So I can, now it's just new, but for 7 years, I can get exactly and analyze this data, which is of course very nice, because then I can show the student how it looks like. But here you see how the voltage looks. And the voltage is in reality extremely little depending on what I'm doing in my house. Because the voltage, since I have a huge amount of neighbors connected to the same feeder, and so it mainly depends on both. I have not analyzed exactly why you get this. Is it my neighbors that is changing their consumption, or is it the feeding point that has this? For example, why do I have such an asymmetry here? You see, it's not exactly the same voltage in the 3 phases. Why I get that, I don't know. It's one of the phases that is continuously higher than the other one, which can depend on a lot of things. Just one thing about the symmetry, I don't know how it is here, but I assume that you have more one-phase distribution here. But in Sweden, we have 3-phase to most households. I'm living in an area where they have houses, and then I think, so it should be rather symmetric. And it is rather symmetric. The lowest voltage here is 229. In Sweden, it's said to be 230. And what you see here is that it's always above. So 230 is here, 235 is here. So it is rather stable voltage, I can say. And I don't know exactly how they control the feeding transformer either, if they match that to the production or consumption. It's here in the morning when people go up. I normally go up at 6. So then because I have an hour of travel from my home to my work. So it's so here in the morning, people are starting to consuming, then the voltage go down, and then they are not doing so much here at the end, and then it goes down. But here is interesting, because here you have a high voltage, even if people come home at 5, 6, 7. And this is, as I said, you have the production up there, and it's very little related to this. what is interesting is that here you have the voltages, and the voltages are of course completely depending on what everyone else is doing. What is interesting here, and that has to do with the converter control. It seems like this, you can do the converter control in different ways, but since what you see here is that you only see one line down there, but that depends on which order they are drawn. They are drawn exactly on the same, so the current is exactly the same in the three phases, but the voltage is different in the three phases. This means, of course, that since the current is the same and the voltage is different, you don't have the same power in the three phases. And this has, to, of course, to do with the converter control. Here you can decide what you want to do. You have the three phases. Do you want to have this? Because you get a certain amount of total power from the solar power. And then, of course, the question is how to spread this out on the three phases. And here they have directly, as we see here they have selected to have exactly the same. I don't know why, and it's probably what's the problem, so to say. I mean, the question is, to be honest, I do not know if you get a problem in one of the phases, what happens. I should try, perhaps just take out one of the fuses for the main fuse and then see what happens with the current, because then it probably splits. I don't know if it shuts down the converter or what happens, because then, of course, it should send out double as much power on the other, or increase the power on the other two phases. But that is, of course, an issue with the converter control, how to change the power from the real production to what you get at the end, what you get out to the grid. Solar power is a bit complicated when you come into costs and economics. First, you have an investment cost, and you have to buy the panels. What is interesting, at least for a country like Sweden, is that even if the panels become free of charge, that doesn't mean that solar power becomes free of charge, because you have to put them somewhere, you have to have a converter, and you have to have people that is putting up these kind of things, or you do it yourself. So, and then what is very important in Sweden is when you borrow money, at which interest rate. Since the solar panel is nearly only an investment, the operation cost is nearly negligible. And then the question is, if you have a high interest rate, then of course it starts to be extremely expensive, because you have to borrow money and pay every year for this money. But in Sweden currently, the interest rate, the national the national interest rate in Sweden is negative. The central bank in Sweden has a negative interest rate, because they want, because from the economic point of view, the inflation should be 2%, but it's hard to come up to 2%. And that is not good, said the economists say. So because of that, we have a negative interest rate. It's rather common in Europe, I think. And I think US, no, they have 0, I think. So, and that has, of course, a big impact on so to borrow money is nearly free of charge in Sweden today. You have to pay it back, unfortunately. And then the installation cost. The question is that in Sweden, most people have a decent payment, which means that they should have a decent payment and I should pay for it. And that means that they just have persons going around, and that costs money. And then you can get a subsidy. In Sweden, I can get that for the investment. And then the question is about, this is one of the important issues. Should I pay to be connected to the grid or not? I think there was some questions around this yesterday, because this is a question in all countries. Who should pay for the grid? It's very easy that if you consume power, energy, you should of course pay for the energy. So there it's very easy, because you consume and you have a producer that is producing. The question is the grid. Who is using the grid? Is it the producers or the consumers? And I can say both. The question is, who is paying for the grid? There you have different strategies. In Sweden, in the Nordic countries, it's both the producers and the consumers who's paying for the grid. So if you have, for example, a hydropower plant in Sweden or a nuclear power plant, you have a grid fee. So you connect to the grid and you pay to be connected to the grid. On the other hand, in countries as Germany, for example, there it's only the consumers who is paying for the grid. Because they say that, yeah, the consumers need the power, of course you need the grid. Yes, but the producers want to sell, so they also need the grid. The question is how to split the cost. And you cannot say that there is some kind of scientific correct issue here. But the issue is here that now I am suddenly becoming a producer because because I have more solar power than I'm consuming. So I'm a producer, I'm selling power to the grid. And that means, of course, that exactly when I send out power to the grid, someone is consuming it somewhere else. So I'm a producer and the other ones are a consumer. So from that point of view, if you start to be big as solar power, then of course you want the consumers to pay for the grid. But that is different in different countries. In Sweden, currently, you don't have to pay with your solar power. You don't have to pay for the extra cost, at least not when you have solar power on your roof like this. But it's that may change. And of course, if solar and wind power let's say if solar and wind power become a very large resource, then of course someone have to pay for the grid. Is it the consumers or the producers? If it's the producers, then the wind and solar power will get an extra cost because you have to pay for the grid. So this is, here we have a lot of, project strategies, how you do this. Okay, so these are the costs. I didn't even have what we had to do in Sweden, and that is a rule because you have some kind of indirect subsidies. For example, we have to change the meter. In Sweden, there is a rule that if you have solar power, you must have a meter that is checking exactly how much you are sending out. Because earlier I had a meter that was only seeing my consumption. But now I have to see that this is I'm consuming and this I'm producing. So you have to have two, and then the question is, how do you measure? Is it per minute, per second, per hour? And in Sweden the rule is that this is per hour. But that you can, of course, have different. I think UK have per half hour, and there is a discussion in Europe to start to measure everything per quarter instead, because you have rather fast, large changes. Okay, so this is the costs, and then you have the income. And this means, of course, that if I consume and then I produce, then the first production reduces my own consumption. So that is step one. And that has, of course, a value because I don't have to buy. And then the question is, how much do I pay for what I'm buying? But then I also get the surplus sometimes. I produce more than I consume. And then, of course, I sell. And that can be different prices. For example, in Sweden, as I said, I'm paying so much for the electricity, and then I pay a tax on that, so I pay so much, and then in addition to that, I pay a grid tariff. I pay for the grid. And if I reduce my consumption, this is how much I save per kilowatt hour. But that is not the same thing as when I'm selling out, because when I sell out, I only have the electricity price, because there is no tax reduction or anything, or a grid fee or anything like this. You could have, of course, a grid fee, so when you are selling, you are paying per kilowatt hour to the grid or something. The grid owner must survive also. But that is not what we have. So reduced purchase is step one. And then you can have maybe a surplus when you are selling out, and that is maybe another price, and that is at what we have in Sweden is that we have specific measurements. So we are so I purchase power when I'm a consumer, and that is reduced. That is one. I save some money, and then I can say that I save money. But then when I sell out, I'm a producer. I was a bit surprised when I started, because the question is who I power to, and then I contacted the company, and they sent a form to me, and then they said that I want your bank account. I'm talking to a retailer. Why should they use my bank account? Yes, because they are sending me money. So there are two things. I'm consuming power, and then I'm selling power. And these are two things, two different things. So what I'm selling, they are not reducing the fee I have. They are paying me money because I sold power to them. So now I'm a producer. I'm a so-called prosumer, producer and consumer. And then, of course, you can have different types of subsidies. That's what we have in Sweden of different kind. But I mean, this you have everywhere. I mean, wherever you are in the world, you have all these kind of things of cost, and then you have the income, the subsidies. Okay, and then in the European system, we have different types of things to handle the environment, and that is one. In Sweden, we have something called green certificates. Green certificates is something that when you are producing power from green sources, from wind power or solar power, or new sources, you can get a certificate. So when you are, let's say, let's say you have a wind power plant, then you are selling your power, then you have a power exchange where you have a price, so you are selling your power for a certain price. But then for each megawatt hour, you also get one certificate, and because you are green. And this certificate you can sell, and then the retailers are in reality have to buy these certificates. So these certificates I get when I produce my power. On the other hand, as a consumer, I have to pay for these certificates. So I'm selling the certificates, but then I'm buying certificates when I'm a consumer at the same time, because that's the way the certificate system works, and it's a way to subsidize the wind power. Then we have another thing, which is guarantees of origin, which is used for so-called green labeling of your power, which these have a significant value. These are really controlling the amount. Today we have 10% of Swedish production from wind power. Without the certificate system, it had been 0. So it's the dominating system that we have in Germany, they have a feed-in tariff. That is what you have in many countries. But where you have a guaranteed price when you are selling your solar or wind power to the grid. In Sweden, we have the electricity price plus a certificate. And it's this certificate, the price level of this one, that have completely controlled that we today have 10% of the power from wind power. And then we have something called guarantees of origin, but that is for green labeling. The value of that in cents or per kilowatt hour is extremely low. So economic value of that is very small. So the question is this profitable for me? This is the preliminary calculation. The problem is that right now I don't know how much I will produce per year, which is one important issue. I have some estimations, but I don't know exactly how it is. The other estimation is that I don't know how much of the solar power production that will reduce my consumption and how much I will sell to other persons. And there are different prices. If I sell to myself, it has one value. If I sell to other ones, it has another value. Say that it takes, let's say this depends. I mean, let's say 14 years it takes me to get my money back. Another way of saying it is that instead of I have so much money, and then I can say that assuming that I have so much money, I put it in the bank. The interest rate in Sweden, if you put money in the bank, is 0 currently, 0%. So instead of having this money put it in the bank, I put it on the roof. And then I get an interest rate of 6.8%. So you can have different ways of calculating. This seems very bad. This seems fantastic. What is interesting with solar power, I have not considered that here, if you want to know more about solar power, is that solar power, the solar cells are not as good after 10 years as they are from the beginning. So you have a decreasing efficiency of the solar power panels. And I got figures for this, so they are guaranteed, the ones I purchased from. I got exactly data. They say that now we have this efficiency 18%, but then after 10 years, I don't know exactly how many percent it decreased. I didn't dare to look on the figure. But so they are not as good after 10 or 15 years as they are from the beginning. Okay, this was just a practical case of solar power, so now I'll go into a bit of more of a analyzing the power system. This figure I have got from it was a German presenter. We had a presentation some years ago, because in Germany there's a lot of solar power. They have around 40 gigawatt of solar power, And the issue happening is that you have the connection here, and then you have the solar power. What is happening is that the further out you are, the higher the voltage become. Exactly as we saw yesterday with wind power, that you get higher and higher voltage when you are out there, and that the same thing will happen if you have solar power. So, and in the difference, I think, with solar and wind power is that solar power, at least in Germany, and that is very common, is connected to the low voltage. So you connect them to 400 volt or 380 volt, as you have here, the line-to-line voltage, the 220 volts. So we are connecting them very far out in the system, compared to, I mean, let's say you have a wind power plant of 1 megawatt or something like this. These you don't connect them on 400 volt or 380 volt. You connect them on, let's say, 10 kilovolt or something like this. And that was the voltage we looked on these. So this is really a low voltage issue. And then the question is, how does that system work? There you have often cables, you have rather thin areas, you can have significant voltage problems out there, and the question is how it works. So the challenge is then how to handle this. Should we close that? So what you have, and here you come into some details, is that I will not go through everything, but it's say something about the PV panels are producing a DC voltage. That's what you get from them. But then, of course, if you connect them, you also get a DC current. Okay, the question is then, which current should you take out? Because you have an impact between the voltage and the current. Then you have something called MPPT, which is maximum power point tracker. What you are doing is that you are maximizing, because if you take out a very little current, because the power is the voltage, the current is in DC, you don't have to consider any phase shifts. So if you have, the question is, which current should I take out in order to maximize the power that I get out from it, from the panels? And that is an MPPT. This was very interesting for my house, because I think I have, 11 panels, I think. The question is, how many MPPTs should I have? That was an issue, because the problem is that if you have, let's say you have one panel like this, and then or you have two panels, and then you get a shadow over one of them, then you try to maximize the power, because then you don't get any voltage from that panel. And then if that is series connected to the next panel, then you get less energy from that panel. So if you have an area with a huge amount of panels, and the question is, how many MPPTs should you have? And that is the problem if you have shadows, and that if you have trees, for example, that you don't get a perfect match. And I have a chimney, and this chimney is then having a shadow over some of these panels. And then was the question, should I have one MPPT? And then I have different deliverers. I asked 5 companies who could deliver solar power to me. And one of them said, then of course we have one MPPT on each one. And someone said that no, and I asked because I learned, I didn't know anything about these details, but then the question was, how many MPPTs should I say? And then they said that, yes, we normally have one. You can get more, but they cost. Of course they cost. And they cost corresponding, each MPPT in Sweden, including VAT and installation and everything, costs, 4,000 rupees around for one MPPT. And that was, of course, a question then, how many MPPTs should I have? Because I can get more power with MPPT, but on the other, more MPPTs, on the other hand, I will pay for them. And then, of course, I can have lower amounts of MPPTs, and I just buy more panels instead. So, but then, of course, I have a limited roof. So that was an optimization problem in itself. I got 2 MPPTs. anyhow, so that is an issue in itself, and that is very much discussed how to do this. There are some ideas about how to improve the MPPTs and so on. That is, of course, it's an important issue how to handle that. Maximum power point tracking. Okay, so that is step one, but that is, you still have DC here. And then the question is, and then you have a lot of different issues, and then you have filtering, because you have power electronics here. You don't want to send out harmonics, which you can do with your power electronics. And then you have this kind of thing here, anti-eye landing, as that came up an issue yesterday, that assumed that my fuse delivers. And then I don't know if the anti-eye landing, if you take one of the phases, what happens. Probably something happens. I have not dared to check, but I'm sure that it works nicely. Then you can have so-called active filter capability, which is discussed nowadays. Since you have a converter, you can do a lot of things. You can, for example, take away harmonics in this kind of thing. You can have grid voltage support. You can have grid frequency support, which is to be discussed, and so on. And so there are a huge amount of controllability. I mean, if you have technically, from that point of view, if you have a solar power that is producing a DC, or if you have an high voltage DC, because you have a converter, so the controllability is the same. You have this pulse wide modulation method that is sending out a sinus curve making a sinus from this one. Okay, so in at least what you can, as I said, you can do a lot of things in this solar power. What is discussed, for example, sometimes is that perhaps you can send out a signal here. I sent a question to these ones and said that, because in one area in Sweden they have said that you are allowed in Gotland, which is an island, they have problems with the transmission there. They have told the company, they have sent out an information that we do not allow anyone to install solar power that is fed into the grid, but it's okay to decrease your own consumption. And then I asked this manufacturer of this converter, is it possible to, for example, but you control, so you are never sending out anything from my house. Is it possible to do that control? And they just said that, yeah, maybe, because then you have to put up a measurements, because then they are not only controlling, they are controlling this, but that will then be based on how much I'm consuming in the house. So then they have an external, and then of course when I put on my toaster, and then you can produce more from the solar power, and then I disconnect my toaster, then they have to decrease, if that is on the margin. So then you really need very fast control in order to do these things. It's technically, I'm sure that it's technically possible to do this kind of thing. It's also the same thing if you have a microgrid where you have a huge amount of solar power. Then you really need to have the frequency, the continuous control from the solar power. And that, of course, is a big challenge. But so there's a huge amount of things you can do in these controllers, of course. Okay, this is just something more about the same thing. But anyhow, I mean, what is happening is that at the final end, you have to send out this power to the grid, and then you have a converter for that. I don't go into all the details here. Just I wrote this here, 50.2 hertz problem in Germany. Let's say you have an isolated system like this, with some wind power and some solar power, and suddenly, and you have a huge amount of production in this area, and suddenly this grid is connected. I can write it like this. Let's say we have some panels here, and we have some wind turbines and some demand here, and you are connected to a grid here in some way, and you are sending out power here, and suddenly you get a problem here. Oof. Then, of course, what happens in this system is that you have a surplus region, so the frequency starts to increase, like this. Then, of course, what will happen? Then you have to disconnect this. This is a problem. So then this is classified as an eye-landing problem, so what you normally do is this. Okay, you disconnect it. The standard rule in Germany is that you have a huge amount of solar power, and each solar power plant has a setting that If the frequency goes up to 50.2 hertz, then we have a local islanding problem, so we disconnect them. The problem nowadays is that in Germany, they have 40 gigawatt of PV. Assume you have a problem in Germany, and you have a surplus production. So the frequency starts to be 50.2, and it's very sunny. What happens? 40 gigawatt suddenly, poof. I'm sure you will get a blackout in Germany. So this is a problem to have very sensitive, because this is a very good idea from the local power system point of view, because if you have 50.2, it's probably an islanding problem. On the other hand, it can also be that we have a severe problem in the country, and then of course if you disconnect like this, 40 gigawatt in Germany, then of course you shouldn't do that. So that was this was identified, because in Germany what happened was that they provided a feed-in tariff which was very high. It corresponds to, what is it? 4 euro per, that's 40, no, 4 crowns per, so it's 40 rupees per kilowatt hour. That was the feed-in tariff they had 10 years ago. That's a huge amount of money. So what happened was that because they thought at that time that this is the cost for solar power. On the other hand, the problem for the German government was that the true price was 20 rupees per kilowatt hour. So it became extremely profitable in Germany to install solar power. So you got, I mean, there came companies and rented people's roofs just to put solar power there in order to make so much money. So that's why they got an extremely fast increase. And then they still kept this issue. They still kept 50.2 as the rule for because of the local islanding problem. But it became, so now they have identified that this is a problem. So you have to, let's say, not only the important thing, you have two issues with solar power, of course, that here we are discussing, okay, the local issue, reactive power and so on, but if we start to say that, yes, solar power sometimes can be 40% of the country's supply, then of course you have to think it as a transmission big issue for the national system. You cannot only see it as a local issue. As long as it is small, and that was what had happened very much both with solar and wind power. In the beginning it was classified that yes, you have a local problem with the voltage that keep the reactive power and so on. But then after a while you have to think about, yes, but now this will be the dominating source in the power system. How should we handle it? And that is a completely different story. I had, because of this, we had a PhD student, Iranian one, Afshin Samadi. He was in Sweden, and what they have, now I will go back to the reactive support. What they have in German is the so-called German grid code for solar power. It works a bit like I showed you yesterday with the wind power. This is the Q and the P. So what is happening is that normally you don't have any Q. You only send out the active power. But when you start to send out more power, then you start to consume reactive power in order to keep down the voltage. Because if you consume reactive power, you keep down the voltage. The question is, on the other hand, how to design this one. Should it be here? Should it be here? Should it be here? Or when should you start to decrease? And then the question is that is what is the standard grid code nowadays in Germany. So if you install a solar power plant in Germany, they work like this, that at a certain amount of active power, they start to consume reactive power in order to keep down the local voltage. Then, of course, the issue is that it's very easy to make a so-called greenfield study. We say that we have a grid like this, and we have a specific situation, then we should do it like this. The problem is that, okay, now we have so much solar power, but in 5 years we will have so much solar power. Should we then change this? Because this is a thing that you have programmed to your converter, that you tell your converter that, please, when you are up to 80% of your solar power production, then you only produce the P. But if you increase even more P, then you start to consume reactive power. So then the question is, how often should you change your converter? Should you change it every day? Should you have a day setting, a night setting? I mean, should they always be the same setting? Because this is, of course, a grid issue, and for each situation, it's easy to say how you should do it. But in the converter, in reality, it's not so easy to change it so often. So the question was both how to do this, and then you can have also different. So what he studied, he made his PhD, what was it, 1.5 years ago, I think. He's working in ABB nowadays in Sweden. So the idea was this kind of coordinated control, and then of course you have to have a control. In reality, this is a controller. Should you have droop control? Should you have? I mean, how should you design the controller? And this is what this person worked with. First, you have this droop-based control, which means that if you can also, another way is to look on the local voltage and then just see what you should do instead of, because this you only say that you should have a certain, at a certain P you should change it. You don't care about the local voltage. Another way is, of course, to look on the local voltage and see, should I have some reactive power in order to react on the local voltage? But then you can get these hunting problems. You have to study the whole system, so you don't get a problem with that. Another issue is, that has to do with equivalence. I just bring it out. Let's say you have an area like this, and here you have the transmission system. What you do normally, let's say we can take a country like India, or as an example. Let's say you have India, just very simple India. It's India. And then you have a transmission system like this, all over the country. When you make a study on this system, which is the natural transmission system, of course you have to model the local grids in some way. And then, for example, you normally have Allahabad here, and that is modeled as, for example, P or Q. The question is how you should model it. If there is a huge amount of solar power in Allahabad, how, for example, should you have P or Q? Should they be voltage sensitive? Because that may happen, because of course you will get different reactive power from the solar power if the voltage in Allahabad is decreasing. So depending on how your system looks like, you need some kind of model for the grid that can be used for other things. So for example, this grid I have here, this you want to model, of course, in some way, maybe as a resistance, or maybe as a P or Q, or this kind of thing. And that is why you need some kind of, I mean, everyone is doing that already today. You are assuming something and you're making something. But that is what we have done here. Develop an equivalent model of distribution grids with high penetration of PV. Because whichever the grid you're working with, you normally have to have a model for the grid below you and perhaps also for the grid above you in some way. The feeding grid you normally have with this short circuit capacity in some way. But the grids which are below you, they have to be modeled in some way. This is an interesting thing that have happened, and of course it should be very interesting to see what happens in the future. This was the so-called solar eclipse that came over Europe March 20. It looks like this. The question is, what happens with the solar power when you have this? And assume that this happens over India, and you have 50% of your production in India from solar power. What happens? I can say the benefit of this kind of thing is that I'm not I don't work with these kind of things, but I'm absolutely sure that if they had computers 1,000 years ago, they could exactly calculate how this will move and when, on the minute. Because, I mean, the globe is moving around. I think it's rather static, not so stochastic. And it's the same with the moon and so on. So they know exactly how this will happen. So this, they knew March 20, 2015, that this will happen. They know a long time in advance. So they could make studies. And they, of course, they are in Germany, so of course they made studies. And the studies, on the other hand, what you don't know is the amounts of clouds. You never know if there will be cloudy a specific day or not, because if it's cloudy, nothing will happen more or less, because then the production goes down to, let's say, 5% or something. It's extremely cloudy. And then, of course, if there is a solar eclipse, it doesn't matter so much because it's no solar power anyhow. So here they made 2 studies here. This is, if it's extremely good, then you will have, then the solar eclipse comes, then it goes down like this, and then the production will go up like this. What you see here is that here the sun, it comes up, but then you get the impact on the eclipse, so then it should go down like this. The interesting thing is this increase here. So this is a very fast increase, and what you see is that in a normal morning, the ramp is like this. On the other hand, after a solar eclipse, this ramp becomes much higher. So it's the ramp here that was the discussion. But anyhow, you should also remember that solar eclipse is a rather slow issue. The solar eclipse is here from 9:45 in the morning. That's what you see here, or you don't see it. Up to, so from 9:45 to up to 10:45, you will get a rather strict ramp. But this is one of the issues. I will come back to that later also. So, I mean, the challenge with both solar and wind power is very much the ramps in some way. But on the other hand, we are never talking about, this is not short-term frequency control. It's not second ramp. It's not ramps on seconds. The challenge here is ramps on, let's say, very many megawatt change per minute or something during an hour or something like this. So here you see the worst case was that the decrease here was 250 megawatt per minute, but the increase was 350 megawatt per minute. And this means that, of course, if you don't have a change in demand, then, of course, if the increase of solar power is 350 megawatt per minute, then other power plants have to decrease with 350 megawatt per minute, which is, of course, is 3,500 megawatt in 10 minutes, which is rather much. On the other hand, of course, if you have a large system, this is what you handle normally also during a day. But the best case, and so-called best case, is when it's not sunny, which is, of course, an interesting challenge. What was interesting here is that this was a real test. This was an extreme test, but this is probably what will happen in the future in Germany. In reality. So this was the studies they made before. They made before this happens. I didn't have this figure. There are some pictures. What was interesting was that the day before, they thought it would be cloudy. So then they saw that, no, this is not a big problem. But when the day happened, all the clouds went away. So they really got something nearly like the most extreme thing. So this, what you see here, is the forecast, is this red thing here. Here you got an increase here of 14 gigawatt of increase of the solar power, and then you got a decrease here of 7.5 gigawatt of a decrease. And you have the measurements. But this, I mean, this just means that you have a good model of what you are doing, because you have to estimate how much solar power you have. An issue with solar power is also the direction of the solar power, which can be a bit difficult, because I mean, if you have south like this and you have the panels like this, then of course you have another issue compared to if your panels is in this direction or in this direction. They are normally fixed. That's the normal way of doing it. Okay, so this was what happened. So I think, and these are things, the interesting thing with this 14 gigawatt of change is, of course, that this is, I mean, if you have the sunrise or the sunset, this is exactly what will happen. I mean, I think India is probably a bit better than Europe, because India is wider. Europe is very much like this. US is better than, US looks like, I have not exactly looked on the distances here, but I mean, US like this. And this, I think that there are 3 hours difference over US. And this means that when the sun is moving like this, if you just have a transmission system like this, then you don't get so much ramps. The worst case is a country like this. Chile, for example, must be terrible. because then you have all the solar power woof, over whole the country, and then of course if you have a transmission like this, it doesn't help you. So it's much better to have a country on this side than to have a country like this. What is there an hour difference in India? It should be, because it's a rather wide country in this direction. It's more wide like this, but on the other hand, I think it's still it should be 2 hour difference or something. Not 2 hours. Okay, but so if you have good transmission like this, then you have smaller problems with solar power if you have it in all over India in this direction. So it's important to spread out. There have been discussions to have solar power around the globe, and then you have a transmission system around the globe also. Then, because then you always have some, but then you get a huge amount of transmission, I can say, on this. So, and Europe is rather, it's very long like this also. You have from Spain, and then you go up to Northern Europe. So Europe is more like this, while US is a bit more like this. So US is better from the solar power point of view. Okay, I just take this, and then I will come into something more concrete. I take this later. We take a small break now, just for 5 minutes up to that, which is completely wrong, but we follow that anyhow. That's another time zone. It's not exactly this time zone. 10 minutes difference. Okay, so we can start again at 22 in just 7 minutes break or something. Just a short break.